I'm Derek Woolverton. I'm currently an engineer at Bloomberg, where I and several thousand other C++ engineers build great, big, giant engines to drive our financial system forward. But that's not what this talk is about. I'm here to tell you guys a story today. And hopefully the story will be useful, and hopefully it'll give us some insight, just a little bit, into the future. It's going to be a work of fiction because, I haven't sat on the standard committee for 25 years or built my own compilers or even my own standard libraries. But I'm just a mortal C++ programmer like most of you. And I've looked at the history of how C++ started and how it evolved, and I realized that there was a story of the evolution of parts of the of the pieces of C++ and how it came together to get us to the point where we are today. And I found that making up these stories was useful because I spent a lot of time early in my career at C++ as a consultant where I got called in because some other team had produced something and then they had moved on or quit or just left behind something, and I got called in to clean it up. Unfortunately, I didn't get to be this kind of cleaner. That would have been cool, but it's more like this kind of cleaner. Right? It was a big mess, and you get to put your hands on the dirtiest, nastiest part and pull. So I'd look at these projects that I'd been called in to work on, and I'd say, well, I can see the lines of code that are here, but can I look at beyond those lines of code and beyond the interfaces and designs, and can I work out what was originally trying to be done? What was the spirit of this thing? And even if the spirit wasn't pretty, just understanding what it was gave me a little bit of a better idea of how to try to proceed with it and how to move forward with the project and not work against it. So I'm going to try to do the same thing with C++. We'll see how that turns out. And my story starts with just some simple classes. We have string, we have vector. Created quite a long time ago, released the standard about 20 years ago. But not ideal. Just a few things, even when they first came out, that were a little disturbing to me. First thing was, these were heap allocated containers. I'm like, you got one string and it's heap allocated. But more troubling than that was the name they put in front of those. Std, we call it. Standard. Not a way to do it. They could have picked a lot of other three-letter acronyms, CPP string, or all kinds of choices. But they picked std to say this is the container. This is the string. This is the way to do things. And the implication of that was that within my own project, I could create any class I wanted or any container I wanted. But as soon as I needed to talk to something else, something from a third party, another vendor, operating system, I was going to run into these types. I mean, who here gets to build a system where you're writing every bit of the system from the first instruction the CPU jumps to when it powers on all the way to the very last thing? Yeah, so embedded, probably. Yeah, it's pretty cool to do that. But most of the time, we're working in a larger ecosystem. And with these types being the standard, the definition of how you're supposed to talk to the system, you became stuck with them. So heap allocation is not fast. And obviously, I jumped ahead. Why am I so upset about heap allocation? Well, I don't need to explain, to some of you already know it's sourceful, but I'm going to let somebody who knows way more about this explain why heap allocation is bad. Turns out in his report on C++, he talked about some of the influences from his days in university working with Simula. And the thing that drove him crazy about Simula was its performance. And he was determined that the major source of inefficiency was its use of heap allocation for all of its objects. So Bjorn's on my side. Heap allocation is not necessarily the best way to go. All right, so we've got these containers. They're on the heap. What can we do about it? Surely somebody came along already and took a whack at trying to fix this. So first thing you can try to do, well, let's try to avoid at least some of the allocations, especially for temporaries, right? So let's see if we can, when we create these strings or these vectors, see if we can share the buffer when we make assignments. See if we can reference count the handles and have more than one copy pointing to the same thing. And then if we modify one of these, then we can allocate more space and give it its own area to work with. This is typically called cow, copy on write. So that was tried, but that had its consequences. You've got complexity. You've got extra space. You've got to keep these reference count, these control blocks. They now have to be independent of the string itself. And every modifying accessor has to go through these pre-checks to say, do I need to fork off the copy I'm pointing to now and make my own independent copy? And unfortunately, you have users who are tripping over the interfaces and often would use a modifying interface, even if they weren't actually going to change the values. This is still happening today. This, Qt or Qt, they were here at the conference last year, and they were talking a lot about the number one problem they have with their own library of containers, which are still copy on write behind the scenes, is that their users are constantly accidentally signaling to the container that they're going to modify it when they aren't really. And so they take performance hits still. So this approach obviously is difficult and fraught with problems. What else do we got? So maybe the optimizers will save us. Compiler writers like to be clever. They like to do interesting tricks. Maybe they can pull something out of their hat and save us some of the pain of these heap allocated containers. So some of the compiler writers came up with return value optimization and other copy elision. But it was not without its controversy even then, because people were writing interesting and clever C++ code that had side effects in their copy constructors and their destructors. And they're like, no, I don't want the compiler to skip that. I put those things in there for a reason. And so this was a big area of tension between the compiler writers who were trying to make things in general faster and certain engineers and programmers who would actually use these features to do curious things. And so it wasn't resolved easily, and it wasn't resolved quickly. Finally, the standard allowed that the compilers could remove those usually unnecessary copies. But they didn't immediately say that it had to. So now you have the problem that you're trying to write cross-platform code. That's one of the benefits of C and C++. But on one platform, it may behave one way, and on another platform another way, or under different compiler options. And so now you have code that is not behaving the same on all the platforms. You've lost that benefit across platform. And it took a lot more time and a lot more pushback from the various parties, and we finally got the standard mandating it in certain cases. But even now, you have this danger, because you might write a function and you follow all the rules and you check it out and it's doing return value optimization today. Well, tomorrow, you have no guard against someone, even yourself, coming in and saying, oh, I need to add X, and accidentally violating the current rules for RVO, and now your function is behaving totally differently. And the performance benefits you got the first time focusing on carefully following the rules and getting it to be set up so that the compiler could do clever tricks with it. Now, it's just gone, and there's no way to say, give me a warning or compile error if I change this code and it no longer can elide the copy. So it's fragile. Hello? Uh-oh. So what else do we got? Well, maybe we can find some interesting hack to take advantage of. A while back, we had the IBM PC come out. The original processor was this cute little thing, the 8088. That's a dip if you've never seen one of those before. 40 pins on there. Not a lot of pins for a processor compared to your modern processor. And so it could only address an address space of a megabyte. So in their infinite wisdom, Microsoft decided, or Bill Gates decided that no one would need more than 640K, famous quote. And the world was happy. But then processors got bigger. That one's got a lot more pins. The computers were still running DOS, and they were still running in a limited address space with only 640K of RAM. Well, the hardware vendor says, well, we got these expansion buses. We could stuff a bunch of RAM chips on them now, and we can put megabytes of memory in your hardware and add it to your PC. Well, okay, how are you going to get it to your software? Well, you've hacked this hardware together. Let's hack the software. And they came up with this hideous thing called expanded memory. Who here had to ever deal with expanded memory? Yeah, it wasn't pretty, right? But it got you this little window into this much bigger, it was like inverse virtual memory, if you can even imagine the thing. And so you could get at this other memory there, and you could get access to megabytes of memory, but it wasn't just a straightforward process to get to any individual byte. It wasn't a flat address space. You couldn't just have an address to memory. And so C and the C++ people said, well, we want to support this. This is a market. And they said, we'll come up with the facility to allow for a pointer type that's more than just an address. And then we'll create this thing called an allocator that could optionally return these more complicated pointer types. And so you could have a container that could allocate memory into expanded memory and use these more involved pointer types to get at it. Well, thankfully, EMS, EMM, that went away. I mean, we got other operating systems besides DOS finally. We got OS2, Windows. And so that part went away, but this facility in the standard was still there. And so some clever people said, well, what if we hijack that? What if we create a temporary buffer on the stack, and then we wrap it up in some kind of magic allocator, and we allocate a container using that stack memory? Well, that's going to be fast, right? Stack's fast, woohoo. And you can pull that off, right? Except that, your programmer never just wants a vector of simple types. They're going to start wanting to compose types. Like, how would you do a vector of string using a custom allocator? It starts to get a little messy. And then, go even further, because no one just uses the containers. Let's say we have user-defined types, and they've got strings inside of them. We don't want to make a vector of those. So trying to get all that allocation machinery to line up with itself and all plug together and actually work, that ended up being requiring quite a bit of cleverness. So again, this was a way to get a little bit more performance out of the system, but it was, again, a little fragile, a little tedious, and not always hooked up exactly the way you thought it was. So, all right, let's check back with compiler people, see if they come up with anything new for us. 2002, sort of the dark ages for C++ standardization. We thought we were going to have a standard out in a year or two, but everyone had to get their feature in. And all these features actually turned out to be far more disruptive and have more unintended consequences than people thought. So Howard and these other people, they were working at MetroWorks on the compiler there, and they realized it's really silly to build these big structures in heap allocated memory and then create a second heap allocated memory and just move everything over to it. Copying when you're just going to destroy the first one, that's really silly. They said, let's steal the memory out of one object. Let's create a mechanism that we could steal the memory out of one object and stick it in the second one. And this overlaps with the idea of temporaries, and it works great for moving the body of one variable over to another. So you can call a function that creates its own local vector, creates a bunch of random numbers, returns it to you, and you just steal that heap from that one and stick it into yours with a string or whatever. But they looked at it and they said, there's even more we can do with this. If we can steal memory from containers, we can optimize all kinds of things. Like if we make a vector, we put 10 things in initially, and then we call resize on 100. Why would we want to copy those first 10 strings over? Well, turns out vector has some peculiar requirements on resizing. Anybody know the stringent requirements vectors have? Have you ever actually had a situation where your application required those stringent requirements? No. I haven't run into it yet. I'm not saying I won't ever run into it, but vector said, if I start to resize my buffers internally, and I start to relocate things, and for any reason something goes wrong, I need to be able to put everything back, throw an exception with the vector in its original state with all its original data preserved. Now, there was a particular group of people who wanted that behavior, but that got baked into vector so that we all got that behavior whether we wanted it or not. Unless you, again, rolled your own. As we saw from the Houdini people, side effects, they just made a vector and they just mem-moved it. And if you put something in there that wasn't trivially relocatable, it just broke. So they're saying, well, this is too good of an optimization not to use. Can we figure out a way to make it work anyway? And so that's how we ended up with more language features in C++11. We got the no except. So you could say, oh yeah, we'll be able to take all the things that were in the original buffer, and we're guaranteed that we can just simply pull them out, call their move constructors, and transfer them over. It will never ever throw an exception. If it does, you can just explode. Problem solved. So we got that additional feature. Which is, it's kind of curious. You went from, you must preserve the original state and give me back the vector to, you can just nuke the whole thing. But we got even more interesting interactions between the containers and C++ features because we added threads. Now, one of the other attempts to optimize a different case for strings was that you could, at one time, represent strings internally as a list or a collection or a set of individual discontinuous pieces so that you could accumulate more and more fragments and then only have to coalesce them into one big piece at the very end when you either copied it somewhere else, or especially if you copy CSTR, you were required to then coalesce everything into a continuous piece of memory with the terminator and be able to present that to the user. Well, then along came threads. And now every one of your containers had to be, we had to review that and decide what operations are going to be expensive and probably not thread safe or require locks around them, which operations are going to be trivial so that you don't have to guard against them in multi-threaded code and you can call them straightforward. Well, CSTR was one of these things that seemed like it ought to be pretty lightweight, that you might be calling it frequently and you really did want to put a lock around it. And even though there was this one corner case of ropes that they were going to need that if they were going to continue to exist, the consensus was, sorry, ropes loses, threads wins. CSTR is going to be a trivial operation, and it's going to be safe to call, and it's not going to modify the underlying object whenever you call it. And so the threads beat the ropes. Well, this had more consequences. like, oh my gosh. When you do that, it's got to be non-modifying, which means the terminator, because this is a C-stir that this is producing, it's got to always be there. So now your string always has got that terminator in its buffer at the end of your active string, even if you're never even ever going to call in your code C-string. And then I don't think there's any compile flag to turn that off. It's just one of those things you get to pay for it. Even more special was C-stir had to work on an empty string. So I've got a string, no space allocated for it, and I got to be able to return you a value. Now, historically, containers didn't allocate any memory when you first started them up. It was fairly inexpensive to create them from scratch. And you could create pretty complex constructs, and at first nothing would happen. So you could create bananas, nothing's in there yet. So no allocations have happened yet. And then you might say, reserve me 10,000 bananas. And in the old days, that was, so far you only get committed to one allocation. A vector that could hold the records, the pointers, and all that stuff for 10,000 strings in bananas. But now under threads, every one of those 10,000 strings had to be ready to return a null from somewhere. So how many allocations was it going to take? And no one wants it to take 10,001 allocations when I make this call. So it looks like we got to go back and figure out something clever to get us out of this bind. So we actually have some bits there. We got a little bucket of bits. Maybe we can hack something together where if the string is empty, or maybe we can actually use that space to store some small strings in place. So this is actually some snippets of the GCC implementation. You've got long, which is your normal structure of a base and a length and a maximum for string. And now you have this thing called short that has a size that's union with a T, so you get alignment worked out. And then this data block with some amount of capacity that can hold some number of T without actually having to go to the heap. So this is good. We can put null in there. And we don't have to, do 10,000 allocations for our bananas. But, okay, what is that capacity? How much do I get? How do I write a program that takes advantage of that or understand its performance implications? Well, this is one of those answers that nobody likes. It depends. If you're using char, there are implementations where you might get 9, 10, 13, all the way up to 22, depending on whether you're 32-bit or 64-bit, and whether you're using a simple implementation of it or more clever, elegant solution. If you're using wide characters, it's really small. You're talking about maybe 4 to 10. And I know some people have been talking about how you can use string to hold other things. And so if you make a basic string of some huge class, well, the compiler people hate you. But they added a case for that. And at least in the GCC version I read through, you're going to be able to fit one regular elephant plus a null elephant in the small string optimization before it'll go to the heap. Which means now your string class is potentially much bigger. I mean, elephant could be any size, right? So you now have size of elephant times 2 as the base size of your string class. On top of, if you have a whole circus of elephants, now you're going to have to go to the heap and allocate a heap of elephants as well. So again, this makes it pretty hard to design and test your performance and your program and understand its performance because this thing is all over the place. But it solved the one problem of the null. So that gets us up to date for the highlights of what we've done to the containers coming up to this point. So where are we going now? Well, there's sharp edges coming up. This is actually my backyard. I had a visitor one day. He was friendly, didn't hurt the dog. We let him swim. He went away eventually. All right. So can we escape the tyranny of the standard containers and heap allocated storage? I mean, what we'd like to do is maybe throw some things on the stack. I mean, occasionally, we're doing the trivialest of string operations. An old tried and true char buffer might be sufficient to do the job. Maybe we want to bring back a classic. Who here did Mac programming way back in the day? Any old Pascal programmers? Yeah, a couple. Stir 255, that was a beautiful temporary variable type. We wrote miles of code using Stir 255. So if we want to use these things, how are we going to pass them to other types? Or pass them to other functions? Well, along comes string view. This is not a new idea. A lot of other platform and internal libraries have this. But it says, let's reduce the interface between one function and another to the essentials. Let's pass the beginning and the end, or the beginning and the length of the memory itself, and not pollute the whole interface with the mechanisms and the representations and the other machinery of the containers. We have this whole issue with breaking changes that trivially change the ABI of C++. Well, if you're just passing two values around, there's no machinery associated with it, you have a much smaller ABI footprint, and it's much harder to break that. String view is designed to work with string and other char types, but potentially, I think you could probably even, if you wanted to be evil, wrap up a vector with it. But again, I don't recommend it, but for those out there who want to be clever and confuse your coworkers. So this is just a safer version of pointers. Some people here at the conference have heard trying to name it borrower type or trying to understand what this is. This is a pointer, or this is the thing like a pointer, except it has more information. So both ends of the memory that you're passing to the other end, so hopefully the other end doesn't run over the edge of the cliff. Since this doesn't own the memory, like a pointer, you have to keep track of lifetimes. This is something we don't always do a great job at. It's a hard problem. Thankfully, we've seen at the talk that there are tools coming to help us identify when we've misbehaved with our lifetime management. Those look like awesome tools. So how should you start thinking about where should you use these types in your interfaces? What would be appropriate? Is it appropriate as an input? Is it appropriate as an output? I've heard various opinions on that, but I like to go back to the old code. There's this whole library of functions that use just straight char pointers, the old C string library. I like to see how they use them and say, does it make sense for us to continue that pattern? There's strcomp, right? Takes two pointers to strings, null terminated strings. So we can imagine an svcomp that just took two string views, all right? And you're saying, well, you can do direct comparison on strings and string views. We might be writing a rocket ship operator for a more complex type and have a function that can return less than, equal, or greater than. It still could be handy. So I can imagine this function existing in some form. We got some more complicated functions. Strchar, take a string and look for a character in it, and do the same thing from the back end. Now, a curious thing here on the C versions is there's a historical reason that they take a const char and they return a char. Now, we're not going to copy that. That was just, there was some really old C code where everything used to be char, and they couldn't break that. C++ has its same problems. But when we write our version, we can take a string, we can pass a string view in, pass in a character, and return a string view that either points at a subset of the string that starts with that character, or we could return an empty string view if we didn't find it. There's a stir that takes two strings. We can do the same thing with string view. I don't know how you'd say that. So you could take the body and again return the string view, which would either be the position in the first where the second string occurred, or or empty if it didn't find it. Here's even this function's stir step. Now, again, this function over here had to do things more primitively because the lengths of strings were intrusive on the storage themselves. If you had a longer string and you wanted to make a substring of that, well, you actually had to go in and stick a terminator in there to cut that string off from the rest of it so you could return it as separate. And this function actually did that. You passed in a pointer to a bigger string and it actually modified the string and put a terminator in there where it found the separation character and then returned the modified, pointing to the new location it found in the original and pointing to the original piece of the newly truncated string in the front. But we have modern strings or modern string views, and we can just say, you started with this much, and I'm giving you back that much. And we don't have to modify the underlying string. So we're actually much better shape here. So again, we take in a couple of string views, return an external string view, or return an outer string view. And I think most people would be able to reason about the lifetime of these objects and how they're operating and be able to use them in the appropriate manner most of the time. And beyond string view, there are a whole host of more types coming along, even more powerful. Span is going to be especially dangerous because it's going to allow you to pass in a range of memory that's modifiable. So you put new values in there, change values, anywhere from the trivial, uppercase my string to sort or anything like that. And it'll work on types beyond just the strings. So you won't have to wrap a vector in the string view. And we got ranges coming with range filters and actions, which now allow you to take a general piece of memory and create a view into that, which is not necessarily contiguous or representative of the underlying data structure, so that you can say, I want you to be able to see, particularly chosen pieces of the bigger picture and just operate on that set alone. And so these will allow us to start with underlying data structures of, immense complexity because we can tune them to the environments that they live in and the lifetimes that we need for those particular things while passing them out into the larger universe of the code without exposing the mechanisms that we're using for lifetime management. So we're separating the lifetime and the mechanisms from the views on the data. And I imagine somewhere down the road, potentially, I hope, fingers crossed, that we get an even more aggressive representation where not only can I change the contents of a structure, but I could potentially shorten it or consume part of it. And somehow, when I'm done with that representation or that proxy for the bigger storage, when that proxy decays, it'll communicate that change to the scope of the ownership to the parent container, and the parent container will do the proper operations to clean up or shuffle around the results to reflect that I've potentially invalidated or used part of those objects. So that's my vision. That's the story I've made up about containers and C++. That's my vision of where I see that story leading us forward. The containers are still going to be part of our lives. Right? We're still going to have stood string and stood vector, and they're still going to be appropriate when we're not in the tightest, most performant part of our code. And that's actually most of the code we write. But that you'll be able to add to your bag of tricks other container types that solve specific needs, that work in specific instances, whether they're temporary, hopefully stack-based objects, or they might be out of a pool of some sort or some other mechanism that matches up with your usage pattern better. And that the interfaces will be so lightweight that they won't care. I hope for a future where there no longer is const string ref as an interface type. because there's so much baggage associated with that. That we move away from passing those things, even the string constructs for the East Coast. But, and that, we'll have to go back to paying attention to our lifetimes. But we already had cases where lifetimes were already tripping us up, where we were already taking references to things, where vector was already moving data out from underneath us. That's not a problem that we didn't have. We just, we could just ignore it some of the time. And now it's going to be one of those things that the C++ programmers that are concerned about performance that we're going to have to pay attention to. And hopefully the tools are going to advance to help us with that added job. So that's my story. Thank you.